Welcome to Mark Jacobson's Masterclass. So I'm just going to introduce Mark real quick. So he is the Professor of Civil and Environmental Engineering and Senior Fellow at the Woods Institute for the Environment and at the Precourt Institute for Energy. So during his career, he has focused on better understanding air pollution and global warming problems and developing large-scale clean, renewable energy solutions to them. Towards that end, he has developed and applied 3D atmosphere, biosphere, ocean computer models, and solvers to simulate air pollution, weather, climate, and renewable energy. He has also developed roadmaps to 100% clean, renewable energy for all purposes and computer models to examine grid stability in the presence of high penetrations of renewable energy. And so we'd like to welcome Mark, and it's going to be a great talk.
Thank you. Thank you all, and welcome to Stanford. And so I'm going to talk about, actually, these are recent plans we've developed for 145 countries that represent about 99.7% of all world emissions to transition entirely to wind, water, and solar energy for all energy purposes. So I'll explain what that means in a second. But I look at this actually from, sorry, I'm going to close this door. Too much noise in there. So I'm looking at it from 3 points of view. I'm really interested in trying to solve air pollution problems on a worldwide scale. There are 7 million people die per year from air pollution. It's the second leading cause of death. And it costs the world, in terms of statistical cost of life, today on the order of $30 trillion per year. And that's, global warming is expected to cost on the order of $30 trillion per year by 2050. So already air pollution is a much more costly impact than global warming, although global warming is catching up, and I'm sure we'll surpass it at some point. And but these problems are interlinked. They're caused by most of the same sources. And energy is the main component, the source of air pollution. Pollutants, 90% of air pollutants that cause human health problems are due to energy, whereas around 70 to 75% of greenhouse gas emissions that affect climate are due to energy. But our plans are really not only to address energy, but also non-energy emissions, although I'll be focusing mostly on energy today. And the other issue is energy insecurity. While fossil fuels are limited resources, they will run out, and that will result in social, economic, and political instability at some point. And so that will cause a lot of internal and external problems in countries around the world. But that's not the only type of energy instability that occurs. You also get energy instability due to the need to, for example, import fuels from long distances away. There are many countries that are in conflict, that have in civil war, or when there are labor disputes, you can have energy shortages due to the fact that it's difficult to transport, or some countries are holding energy hostage versus other countries. Another type of energy instability is the fact that you have a lot of centralized power plants or refineries, and if one goes down, that takes a big part of the grid down, as opposed to having more distributed energy, such as wind and solar, where you have lots of individual wind turbines or solar panels that can increase the ability to keep the grid operating when you have something catastrophic happen. Anyway, there are other types of energy instabilities as well. But so our goal is to try to solve all three of these problems. And you'll notice that if you just try to solve the climate problem alone, that's a different solution than if you try to solve the air pollution, climate, and energy insecurity problem together. They're actually, because a lot of proposed solutions that you hear about today, I mean, many of them actually do not address air pollution, do not address energy insecurity. They just make these problems worse. And I'll just throw them out here right now. Carbon capture is one. Increases air pollution, increases energy insecurity by allowing fossil fuels to persist, and in fact increases their energy requirements by about 25%, to 30% actually. 30% more energy to run carbon capture equipment. And that means 30% more fuel, 30% more air pollution, 30% more mining. Anyway, that's just one, but maybe I'll get into other ones as well. Anyway, our goal, though, is in order to solve these problems, we want to focus on what works and what can be implemented quickly, what has low cost, and what is most efficient, it turns out, is electrification of just about everything. So electrifying transport, electrifying building, heating and cooling, electrifying industry. So for transport, we go to mostly battery electric vehicles for pretty much all passenger vehicles, all short and medium distance ground vehicles. And then we reserve for long distance heavy transport, like long distance aircraft and even some mid distance aircraft, but long distance ships, long distance trains, and some long distance trucks, hydrogen fuel cell electric vehicles, and where the hydrogen is produced only from clean renewable electricity, so that's called green hydrogen. And I'll show you an analysis where, because some people will say, well, why not just use battery electrics for everything? I mean, if we could, we should. But it turns out, like when you have like long distance transport, you're just using a lot of energy carrying the batteries around. The further you want to go, the more batteries you need, the more you're just using energy just to carry the batteries. So there is a crossover point in terms of distance where hydrogen fuel cell actually becomes more efficient. Otherwise, like for passenger vehicles, an electric vehicle is 3 times more efficient than a hydrogen fuel cell electric vehicle. In other words, you need 3 times the number of wind turbines to go the same distance. But there is a crossover point when you get to longer distance heavy transport. For buildings, we want to go to mostly electric heat pumps for air heating, water heating, air conditioning, even dryers, electric heat pump dryers for clothes drying. And there'll be a certain fraction of heating and cooling that will be what's called district heating and cooling. I mean, so that's where you have centralized heaters and coolers. In fact, this campus is running on district heating right now. And I'll discuss that in a minute. But that's good. District heating is good when you have a urban population or in cities. I mean, 7% of the U.S. is under district heating right now, but 50% of Northern Europe is in district heating. So it's good for certain applications, but not so good for rural areas. So in rural areas or suburban areas, maybe you'd have individual heaters, heat pumps for heating and cooling. So geothermal heat and solar direct heat, we'll use those as well, but those would be feeded mostly into district heating and cooling, district heating systems in this case. For industry, we'd electrify that for high temperature industrial processes, use electric arc furnaces, induction furnaces, resistance furnaces, dielectric heaters, electron beam heaters. These are all existing technologies. In fact, pretty much everything we need is already present. We have about 95% of the technologies we need to transition the world entirely to clean renewable energy and storage. What we don't have are, for example, long-distance aircraft, like hydrogen fuel cell, long-distance ships. But we know how to do that, and we have the technology to do that, but we just don't have them commercialized. And also some industrial processes haven't been transitioned. Now, so we'll need a lot of electricity, and we'll obtain that electricity entirely from onshore and offshore wind, solar photovoltaics on rooftops and in power plants, concentrated solar power, geothermal electricity, existing hydroelectricity, mostly existing hydroelectricity, and some small amounts of tidal and wave power. So this is basically, this is kind of a summary of everything you need in terms of generation and the main equipment. We also need storage because the wind doesn't always blow, the sun doesn't always shine. So, it'll be interesting because when we actually electrify all energy sectors, it makes it easier to match power demand with supply on the grid, it'll turn out, due to what's called intersector coupling of these different energy sectors. But we will need electricity storage, heat storage, cold storage, and then hydrogen as a form of storage. But there are many electricity storage options that exist. Concentrated solar power, CSP, with storage. Pumped hydroelectric power is the largest source of storage in the world today, of electricity storage aside from actual hydroelectric dams, which are also like big batteries. Batteries themselves, flywheels, compressed air storage, and gravitational storage with solid masses, which I'll mention in a little bit. For heating, cooling, which is actually low-cost storage. There's water tank storage, storing hot water and cold water in water tanks. It's pretty inexpensive. Ice storage. Actually, Stanford used to, in 1998, there was a big ice cube constructed. Well, there's an apparatus to form ice under a building. And so at night, when electricity prices were low, the electricity was used to produce the ice. And then during the day, instead of running air conditioning during peak times of the day, when you might have blackouts occur, you'd run water through the coils in the ice and send the cold water to buildings. And so that's a kind of district cooling system that actually is pretty common in stadiums and in hospitals. It's used quite a bit around the world, ice storage. But there's also underground heat storage in boreholes, water pits, and aquifers. And I'll talk about that in a minute, too. I mentioned hydrogen. Well, so this is Stanford's district heating and cooling system. It's actually the first district heating and cooling system in the world. That defines fourth generation, having both heating and cooling. And actually, as of a couple months ago, Stanford is also the first university in the world to be 100% renewable, not only for electricity, but also heating and cooling. Actually, it was a couple of years ago so to power the university electricity, like the lights and everything else, including the district heating and cooling system, well, Stanford purchased 150 megawatts of solar, so 10 megawatts on rooftops on the campus, and then 2 big PV power plants in the Central Valley. But actually, 2 years ago, one of the PV power plants burned down during a fire. So it had been 100% renewable, but then it was not. But then it just rebuilt the PV plant, and now it's back to 100% renewable. And so this district heating and cooling system, it replaced a natural gas cogeneration plant, which actually used to be located right across the street, just down a block at the corner of Campus Drive and this street out here. There was a gas cogeneration plant that provided 80% of the campus electricity and heat. And that was bulldozed and replaced with this system, which is further down there. And so there are 2 chillers and a boiler. There are about 35 miles of cold water pipes and about 40 miles of hot water pipes around the university that, because at any given time, different buildings need either hot or cold water or air. And so the hot and cold water are stored and produced in these boilers and chillers. There are heat pumps, electric heat pumps used to raise the temperature of the heat or to lower the temperature of the cold, where the electricity comes from the solar. And there's recycled heat, because when you produce heat, you have waste cold, and when you produce cold, you have waste heat. So instead of letting that just go to the air, it's recycled and sent to the respective tank. So it's a very efficient system as well. And so most all the buildings are under this district heating and cooling system, but not all of them. Their campus is not entirely zero carbon, because there are like 250 diesel generators around the campus for backup power, and we need to get rid of those as well. And there's many of the vehicles, like the buses, you can see are electric buses, but there are some that are still, I think, natural gas, or they have some vehicles that are not all electric. Anyway, so there's some ways to go and a few things, but in terms of heating, cooling, and electricity, it's 100% renewable. This is another type of district heating system. This is in Okotoks, Canada. In 2004 and 5, there were 52 homes built with solar collectors on their roofs of the garages, as you can see in the top left. And those solar collectors contain a glycol solution. So during the summer, when the days are long, sunlight hits the glycol solution, it heats up. That solution is then piped to this building on the right, and the heat is transferred to water. The water is then piped under this field. This is just a play field that had been excavated, and these boreholes were drilled about 30 meters down, and U-shaped pipes were put in. So the hot water goes down, and the heat is transferred to the soil to heat up the soil, and then the water comes up cooler, and then the water then goes back to the building to get reheated. But that heat is stored for up to 6 months in the soil, and the soil temperature can get up to 80 degrees Celsius. But on the surface, it's insulated on the top. On the surface, you can't feel it, and you don't even know there's a storage system underneath. In fact, there are kids playing on this field. And then in the well, all year the heat is recycled, but there's also a boiler inside that building that most of the heat is coming from the boiler. But during the winter, when the snow is on the ground, then you need to take out some of this heat. And so you send cold water down, heat gets transferred to the cold water, and then the cold water gets piped, the hot water gets piped to the buildings. And this heating system supplies 100% of the year-round heating for these 52 homes. And the cost of the storage is phenomenally low. The actual storage is less than $1 a kilowatt hour. I mean, batteries are like $150 a kilowatt hour. We're not talking about electricity storage, we're still talking about heat storage, but just in terms of energy, it's like less than $1 a kilowatt hour. It's not that expensive to do this. And there are many of these systems around the world. This is another type of district heating system, water pit storage. It's a similar idea, but here you have this kind of big swimming pool on the left that gets filled with water and it's covered with insulation. You don't see that right now, but these solar collectors on the right will send heat to the water, and that water will be heated up to 80 degrees Celsius. You don't want it to get to boiling point because then it corrodes the lining much more and it starts evaporating too. But so that heat is then stored for up to 6 months, and then it supplies much of the heat. Well, Vogens, Denmark, it has like 2,500 buildings, residences, and this supplies like about 70% of the heating for the residents of this community. So this is, this is less than $1 a kilowatt hour of storage. It's really inexpensive type of storage. So district heating is it's actually a very good way to provide heat for a community. Yeah, question?
We are keen to ask the questions.
Yeah, sure. Yeah.
And what's the efficiency of such storages?
Well, the efficiency of the borehole storage with the soil, it's not very. It's like, I think it was like 58% from the heat collected in the summer to what gets returned in the winter. It's only 58%, but at less than $1 a kilowatt hour, it's not, materially.
It's renewable.
Yeah, and it's like there's plenty of it. You're continuously collecting the heat. So yeah, it's not that efficient. And this is, I think, a little more efficient, but because you're storing it for so long, there are heat losses. So it's on the same order, but again, it's the same low cost. Yeah, back first.
Question. When you say $1 per kilowatt hour, is that levelized cost or like overnight installed?
No, that's the levelized cost of energy from the because that's the levelized cost in that case. Question.
Is there a way to do this but for cooling?
In fact, you could. Well, the one I'm not going to show is the aquifer storage, which is, they have it in several places in Europe, where you have an underground aquifer under some bedrock, and then there's water level. What you do is you actually have two sides. You take, on one side it's for cooling, one side's for heating, and you have pipes going up. And so in the, let's say in the winter, you want heat, so you transfer hot water from the hot water side, and then you heat the buildings, and then you send the cold water that results down to the cold water side. And then in the opposite season, the summer, you take the cold water from the cold water side and you move it to the hot water side. So
it conserves the temperature, like when it's underground, so you can kind of adjust based on whether you need heating or cooling.
You could, like, if you have to have them far enough apart, because you're going to have diffusion of heat. Like even in the aquifer, I mean, it's water, so you do have some diffusion of the heat, but it's relatively slow. And so I think you could do it in soil. Not with the water pit storage, it's not as easy. But I mean, ice storage is definitely like a cooling storage system. Now with underground borehole storage, you could do two sides where it's cold and hot. But I haven't heard of any cold storage in soil, just in aquifers. Yeah.
With either cold, with like hot storage, in soil have any adverse effect on soil chemistry and also micro ecosystems within the soil?
It's possible. But these are an aquifer. The place that they do the aquifer, they're under this rock, so it's pretty deep down. I mean, it'll just be a thermal effect because there are no chemicals involved. In the borehole cases, again, it's just heating the soils. So, and then they insulate around the whole thing on the sides. There probably are thermal effects, but again, no chemical effects that I'm familiar with. Yeah.
How big is the water pump? How big is it? What's the ratio of the size of the pump to the number of the resident?
I don't know the number offhand, but this one you can actually, it's probably the specs you can look up. Just look up this Vogen's water pit storage. And
Yes, if it is in the city, the land value is really high. It's like if it's a huge thing, it's probably a problem to face it.
Yeah, anything. I mean, yeah, it does take up space. I mean, that's not one thing about the borehole storage. It's nice because you can put it under like a field and you can use it for multi-purposes. And the collectors are on the rooftops of garages. So I suppose here you could distribute the collectors on rooftops as well. I mean, you can see from this, the most of the space is taken up by the collectors, not the actual water, the storage part. But yeah, I mean, anything with solar, it's going to take up some area, but the more rooftop we can do, the less land we have to take. All right. Well, here's the ice storage, by the way. This is where I gave you the example. You have these coils in the ice that you send the water through to cool, and then you send cold water to the buildings. So, but this was around $30 a kilowatt hour of storage, of actual storage capacity. So I think when you asked that question about whether it's levelized cost, I think it might be. I don't know about the borehole, whether this, like this though, it's like when I say $30 a kilowatt hour, that's the capital cost, kilowatt hour of storage. So in terms, I think actually it's also the $1 kilowatt hour is probably also the capital cost. But I know for batteries, it's capital cost is like $100 to $150 a kilowatt hour of capacity. Yeah, quick question.
Quick question about ice storage, because water has this property to kind of expand and be cooled beyond lower than 4 degrees Celsius. So would the constant expansion and contraction have any adverse effect on the I presume copper heat exchangers?
Well, I would assume like this is open on the top, so like the expansion would occur. It's not constrained. It's not like in a box. I would think if it were in a box where it couldn't expand, then you would have that problem. You'd probably squish the pipes. But I think this is, it's free to expand upward in that case. Although you can't read this, I thought this was actually cool. This is from a student of mine who's in the Army who we looked at transitioning all military vehicles to either electric, battery electric, or hydrogen fuel cell electric. And the goal was to see, well, is it technically feasible to transition all vehicles? And then we also added in here like a 747 aircraft and big ships and stuff like that. Well, I just want to show you this. This one is for a 747. So the idea was to see, can you conserve properties, like especially in the military, you can't have like a tank that's much bigger than a current tank because you can't fit under a tunnel. It can't be too heavy because you have to go across certain bridges and it'll collapse. So you have to try to conserve like mass, volume. We also want to conserve distance or range, and also what's called the power to weight ratio or the thrust to weight ratio. That's more important for aircraft, for example. But anyway, this is for a for 747. What this means is just look at these black lines versus 100%. So this is conserved at 100%. You're conserving all these properties. This one is this is mass. This is volume, and this one's range. This one's range, and this is the thrust to weight ratio. But what this is saying is, for a 747 with this is with hydrogen fuel cells, you can conserve the range and the thrust to weight ratio, but at the expense of a slightly larger, about 23% larger volume, but about 21% lower mass. So this was like actually going into an airplane and actually exchanging all the components that you need for a hydrogen fuel cell aircraft versus a fossil fuel, jet fuel aircraft, and then looking at the resulting mass and all these properties. But the point was, that's based on published technology that's feasible. It's not existing right now, but published in the published literature what's feasible. And so that indicates that with you could run a 747 on hydrogen fuel cells. We found out we can't do it with batteries, but you can do it with hydrogen fuel cells. And in fact, we can run everything like Abrams tanks and ships and helicopters and propeller planes and locomotives. Everything can be run with a hydrogen fuel cell, and several of them can be run with batteries as well, but not all of them. So, which is good news. I mean, there's the good news is you can do one or the other, and we want to do planes. I mean, some people talk about, well, why not use like biofuels for airplanes? Well, biofuels still pollute, and they still, when you burn a biofuel, you still have many chemicals coming out. Still results in air pollution. You still get contrails. When you have an electric airplane, you have no more contrails. When you have a hydrogen fuel cell airplane, the only thing that comes out is water vapor. So you do still get, because a contrail from an aircraft forms when you have particles coming out of the aircraft, and then you have water vapor from the aircraft, and the water vapor condenses on the particles. And so you get a lot of small particles that they're liquid at first because it's high temperature, well, they're gas, and then it condenses, and then eventually freezes when it dilutes enough. So you get ice particles. When you only have water vapor coming out, the water vapor can only condense on background particles. So you get many fewer condensation particles. And so you end up getting like 10% of the contrails with hydrogen fuel cell than you do with jet fuel. But so if you use a biofuel airplane, you're still getting black carbon, which is the second leading cause of global warming after carbon dioxide. And that's soot particles, basically, that come out, and you not only get contrails forming on them, but the soot evaporates clouds, it settles onto the snow and melts the snow and sea ice, and it absorbs sunlight directly, and then that's why it's black, because it absorbs sunlight directly, doesn't allow sunlight to penetrate. It heats up when it absorbs the sunlight, and then heats the air. So it's actually 1,000,000 times more powerful per unit mass than carbon dioxide at warming the air. And cross-polar flights are particularly a problem. And cross-polar flights only started in like late 1990s when Russia allowed cross-polar flights to occur. But since then, aircraft are actually the main source of black carbon to the Arctic, because they're flying only 10 kilometers above the Arctic, and all that soot just drops in, and then it just melts the snow and the ice. And so actually the reason the Arctic is heating up much faster than the rest of the planet is due to what's called the snow albedo effect, which is due to a combination of carbon dioxide acting as a blanket and heating up the snow and the sea ice, melting it a little bit, and then uncovering darker surfaces below. Like when you have snow on top of sea ice, on top of water, on top of seawater, the albedo or reflectivity of snow is about 95% of new snow. Sea ice is about 65%, and seawater is about 6 or 7 or 8%. So the more you melt, the darker the surface is below, the less reflection you get, and the more the positive feedback of warming you get. So CO2 does that, but black carbon does that even faster, because it not only heats up the air right above the Arctic, which then translates to the ground, but it sits on the Arctic and then melts the Arctic. Sunlight hits the black carbon on the snow or the ice, and then you just get melting right around where the soot particles are. And so that's one of the causes why the Arctic temperature is now 5 degrees higher than it used to be, whereas the average global warming so far is about 1.1 degrees Celsius. So anyway, my point is we don't want to use biofuel aircraft. We want to go to electric or hydrogen fuel cell. Yeah, question?
Biofuels also way less fuel efficient than like normal fossil fuels.
Yeah, they are less efficient in terms of the energy that they contain, and they also require lots of land to grow, and you have energy to process it, stuff. But that hasn't stopped people arguing that, because you take CO2 out of the air to regrow the biofuel, they're saying, oh, it must be CO2 neutral. It's just not. It takes a lot of energy to actually produce that biofuel and refine it, and get it to the market.
Especially with like ethanol.
Well, ethanol is even worse. Because you can't even put ethanol, at least oil you can put in a pipe. You can't put ethanol in a pipe, so you have to train, truck, and barge it around, and that just emits lots of diesel exhaust because all those are run by diesel. Anyways, okay, so I don't want to take up too much time, but I'm going to talk briefly about transitioning individual buildings, then I'll look at plans for all the countries. This is actually, I'm going to talk about my own home, which I built 5.5 years ago on campus, and it's all electric, it's no gas, and it's kind of an experimental home to see, well, can you actually just, what would happen if you try to build an all-electric home with all these technologies. So it has solar on the roof. It's like 13.6 kilowatts. And there are batteries in the garage that each one is 3.3 kilowatts. And there's about 2 hours of storage at full discharge rate, so 6.6 kilowatt hours. And you can multiply by 4 to get the total. But the way they operate is in the morning, sun starts providing electricity through the panels. Household electricity is met with the solar directly. The excess goes to the batteries. So the batteries are filled starting in the morning. When the batteries are filled and no more electricity is needed for the home, the rest gets sent to the grid, and I basically sell the electricity to the grid. And then at night, when the sun goes down, the batteries kick in and provide electricity for the home. And often they don't run out. You can run them all night and there's still something left in the morning. But other times, like especially in the winter, it gets depleted. They get depleted in the night, and then I do use grid electricity. But on average, over 5.5 years, it's been I've produced 20% more electricity than I've consumed. And this is with 2 electric cars as well. But for heating and cooling, I use what's called a ductless mini-split heat pump for air heating and air conditioning. And so there are these 11 of these inside units on the left, and there's 2 of these outside heat exchangers. And there are no ducts, which are these big metal tubes where you send heat. Like if you have a centralized heater in your home, you'll produce heat, let's say in the garage, and then you'll send the heat through these ducts to different rooms. Here, each of these units just provides heating and cooling for the individual room. And the only thing between the inside units and the outside units are small flexible tubes containing a coolant. So heat pumps do not create heat, they just move it around. So as a result, they use 1/4 the energy as a natural gas heater. So they're very efficient because you're not burning anything, you're not actually producing the heat, you're just moving it from the outside, in this case, to the inside. And this is called an air source heat pump because it's taking the heat out of the air. If you take it out of the ground, it's a ground source heat pump. If you take it out from water, it's a water source heat pump. Ground source heat pumps used to be really expensive, but now actually there's like a company in New York called Dandelion that they drill vertically, kind of like with the borehole storage, but just one hole down, just one really small hole down, 30 meters, and they extract the heat from the soil. And the nice thing about that is that the soil's always warm all year, even if there's snow on the ground. So if you have a ground source heat pump, that uses about 1/5 of the energy as a natural gas heater. An air source heat pump's about 1/4, or it could be 1/3 depending on the outside temperature. But anyway, so it uses very little energy. For water heating, I use a heat pump water heater, which in this case, it just extracts the heat from the room that the heater sits in, where those vents are. So the room becomes a little cooler. So in the summer, I just open the door and that cool air can help air condition the house as well. But again, it just uses coolant and a compressor to compress air to heat it. And the coolant also, when you condense, you release heat. Yeah.
How was it working during the heat wave?
Oh, it was amazing, actually. I actually, the hottest day of the heat wave, I sent 30 kilowatt hours back to the grid. Yeah, and the temperature in my house, I kept it 76 degrees, 76 Fahrenheit. It was perfect. I mean, that's why I'm saying it's so efficient. These new technologies are just so efficient. If everybody had this in their homes or buildings, yeah, we wouldn't have any blackouts for sure. In fact, I think I'll show you Yeah, in fact, I have one from a couple of years ago, a similar heat wave. I'll show you the actual diagram in a second. For cooking, instead of a gas stove, I use an electric induction cooktop, which is not an electric resistance. A lot of people don't like electric resistance stoves where you just get the red burner. You turn it on and it's red. The way this works is you have to have a pot or a pan with a iron or stainless steel base that has high resistance. So there's an electric current running in each of these little burners, when you have a pot on it. And that electric current induces a magnetic field. And that magnetic field will then induce a current. Well, it's a fluctuate because it's AC electricity. It's a fluctuating magnetic field, and the fluctuating magnetic field will induce a current in the pot itself. So a current starts going in the pot, but because of the high resistance, that current gets dissipated to heat. So the pot heats up very evenly, and you can control the temperature really well. But this boils water, and half the time is natural gas. And the temperature is really easy to control. Plus, if you touch the stove, you don't burn your hand, even when you're boiling water, because you're not heating the stove, you're heating the pot. The pot will send some heat back to the stove through just conduction, but it just makes the stove warm. It doesn't make it really hot. Anyway, it works perfectly. I show that burner on the left because I mentioned earlier that 7 million people die from air pollution each year. Well, 40% of those are from indoor burning of biofuels and coal for home heating and cooking. And one of those burners, individual ones, that cost between $30 and $70. And you can plug them in to the wall, and you don't need to burn wood or biofuel to provide heat. Now, you do need electricity, of course. So a lot of communities don't have electricity, so the idea would be to provide what's called a microgrid for communities, remote communities, where you have a combination of some solar batteries. That's all you need, really, solar and batteries to provide some basic electricity for lights and cooking. Well, anyway, here's a summary of 5 years of use. Generated 120% of all home and vehicle energy. No electric bill, natural gas bill, or gasoline bill. And I received about $860 a year from the Community Choice Aggregation Utility, which is in this case Silicon Valley Clean Energy, who takes over the generation portion of the electric bill. PG&E in this area runs the transmission distribution lines, so they still take over they still have the portion of the bill is transmission distribution, but the Community Choice Aggregation Utility, which there are 7 states in the U.S. that allow community choice aggregation utilities, and California is one. They're amazing because they'll not only pay you for the extra electricity at the rate you would have had to pay for that electricity at the time of the day you produce it, but let's say you're in an apartment and you don't even produce your own electricity, you can purchase 100% renewable electricity from them. So that's nice. A lot of these CCAs will have 100% electricity renewable options. But I avoided a gas hookup fee. PG&E was going to charge $6,000 just to hook up gas from the edge of the property to the property. And there's no reason for it except that they can do it. So that's a cost that it was avoided, about $10,000 in pipes. So this just shows typical ranges that people would save on these things, but the total is about $5,000 to $23,000 up front and $3,000 to $10,000 per year. Now, there are subsidies available, especially with this new Inflation Reduction Act, for doing all this stuff. So, and I had some subsidies coming in, but I already paid this back in 5 years. There's a payback with the subsidies. Without subsidies, it would be 10 years. But like the solar is warranted for 25 years. So right now, for the next 20 years, it's just free energy. And it's just from a financial point of view, there's just no reason not to do this for every new building. It's a little trickier for existing buildings, but it can be done for existing buildings as well. Replacing heat pumps, you just replace anything that you're using gas with electric equivalents. So here's the hottest day of the year in 2020, September 6th. It was 106 degrees outside, 77 degrees inside. So the green is solar production during the day. The blue during the day is just the solar use for home energy, electricity. Most of that's for the cooling. And then the blue at night is when the batteries kicked in and then mostly ran the cooling, air conditioning. Then the red is when the batteries ran out and I needed grid electricity. But from the data on the top, you can see that I produce almost 60 kilowatt hours, and I consumed 45 kilowatt hours. So on that day, it was 15 kilowatt hours were sent back to the grid. And this is a day where there were blackouts in California. So it's definitely worthwhile. But the other thing is you'll notice, well, okay, there's a lot of solar that's gone up in California, but at night you'll suddenly have you have a lack of energy. What do you do at night? So, well, one thing they're doing is that California's now put in about 2.3 gigawatts of batteries. So they kick in, 2.8 gigawatts, almost 3 gigawatts of batteries. The peak demand, the peak load in California this last week, it was the highest load ever. It was like 53 gigawatts. Normally it's about, 20 to 25 gigawatts is the average load during the year. But during the summer, the load is the highest, and it got up to 53 gigawatts. So the batteries provided 3 out of the 53 gigawatts after the sun went down. The solar during the day provided about, I think it was somewhere between 18 and 20 gigawatts. So there's a lot, solar and wind to combine. So renewables, on average in California, are over 50% in the annual average. But during this peak summer, it's closer to 35, 40% or something. But what do we do at night? Well, fortunately, these are offshore wind data. This is from another student from a few years ago, from Northern California near Mendocino. Well, this shows hour of the day, and there are 4 lines here. There's one's representing each season. So there's July, October, January, and April. Well, you see July is where you have the highest wind speeds offshore California. And then the wind speed also goes up a little bit during the night. So this is the ideal solution because that's when the highest demand for electricity in California is by far is during the summer, and then summer nights or just as the sun goes down is when you need it the most, and that's where we can use offshore wind, which is one of the reasons why it was so annoying to see Diablo Canyon being extended for 5 years, because Diablo Canyon is one of the few places in California where there's actually electrical transmission line right to the coast. And there's a plan, the Biden administration has a plan to put offshore wind offshore of California, and so does California. But the 2 locations are right where Diablo Canyon is located because they have that transmission corridor, and up in Mendocino near here. And since Diablo Canyon was extended, that means there's going to be no offshore wind off of California in central California for at least 5 more years. So that's just, it really set back the ability to, and plus they're spending $1.4 billion up front just to subsidize it staying open, and that could have been used to pay for this new wind, which we're going to need anyway. So it's just kind of completely misguided policy when you really need to build out this offshore wind, because there's enough offshore wind out of California to power the entire state. In fact, the whole western U.S. So there's so much potential. Anyway, I want to talk about transitioning to 145 countries, these plans that we've developed. So we looked at, we started with IEA, International Energy Agency data for 2018. We're looking at end-use demand in all the energy sectors. And if you sum over all countries and all end-use demand, there's in 2018, it's about 13.1 trillion watts in the annual averages being used of power. And that's expected to grow by 2050 to 20.4 terawatts. However, if we electrify all energy and provide that electricity with wind, water, and solar, that can go down by around 56% to 8.9 terawatts without people changing their habits. And the reason is, well, I mentioned heat pumps. Heat pumps are much more efficient than gas heaters because you're not creating heat, you're just moving it. So you use like 1/4 the energy. But averaged worldwide and overall energy sectors, that's about 13.6% reduction of power demand due to using heat pumps everywhere. Same thing with electric vehicles. They're much more efficient than gasoline engines because, only 17 to 20% of the energy in gasoline goes to move a car, and the rest is waste heat. Whereas in an electric car, about 80 to 86% of the electricity that goes to move the car. That's why it accelerates so well. But averaged overall countries and overall sectors, it's about a 20.5% reduction of demand there. Another 4.3% reduction due to electrification of industry. And then most people don't realize, but 11.3% of all energy worldwide is used to mine, refine, and transport fossil fuels and uranium. And so we can eliminate that energy just by going to wind, water, and solar, because wind comes right to the turbine, solar comes right to the panel. You don't need to dig it up. And then we think we can squeeze another 6.6% energy efficiency improvements beyond business as usual. So that adds up to 56% reduction. So this is kind of a transition timeline, well, starting at 2020 to 2050. If we don't do anything, we go along the top line of worldwide, I'll call it worldwide since it's about 99.7% of all energy, up to 20.4 terawatts. But if we electrify everything, we go down those 5 shades of colors due to the reasons I just mentioned, down to the 100% WWS line of 8.9 terawatts. And then we would provide all that resulting electricity with wind or solar, geothermal, hydro, etc. And we propose we need a transition of 80% by 2030. So that's within 8 years, which is another reason we cannot use technologies that will take 10, 15 years. I mean, the average time it takes between planning and operation of a new nuclear plant, anybody know? How long is it?
20 years?
It's right now, it's between 15 and 21 years. And in the U.S., the only plants being built are in Georgia, the Vogtle plants, and they're on years around 17 to 18. Finland, they just finished one after 21 years. Then they opened it. It shut down again a few weeks ago because one of the turbines broke. And so now it's going to be down for another 8 months or something. But it should be fixed. But still, it's 21 years to operate. The Flamanville, France one is on year 18 or 19 and still delayed. The Hinkley plant in England, that's going to take 20 years. There's no nuclear plant anywhere in the world that's ever taken less than 10 years between planning and operation in history. Even in China, where they're putting up a lot more, they're taking somewhere between 11 and 16 years for those plants. Yeah.
Just to clarify, to enable this vision, this gigawatt value is an average power demand?
Yeah, this is an annual average power demand.
Annual average, okay. And how much storage is required to do this?
If you want the storage numbers, I can point you to the paper that actually has them for each country and each region. But it's a lot. But the cost, I'll show you the cost with the storage accounted for. They don't give you how many gigawatts, but I can give you those numbers. Yeah.
Yeah, just interesting to point out that till 2030, is 80% of the transition, and then the next 20 years just waiting.
Right, so that's why I have this slide here, which is, okay, why wait till 2050 to get to 100%? We really should.
Or it will not be 80% till 2030.
Yeah, so this is a goal rather than what actually will happen. This is what we're saying should happen. This is what we should shoot for. So, yeah, you're right, though. If we get 80% by 2030, why should it take 20 more years to get the last 20%? Probably going to take faster. So that's why, and the only reason that was assumed that it would be 100% by 2050 is because that's pretty much everybody's deadline that we hear about. But in reality, we can get it, if we get 80% by 2030, we should be able to get the rest by 2035. Because what's left? It's these long distance aircraft and ships, and we, from today, we think we can do that within like 12, 15 years. Yeah.
What is the reasoning behind trying to get 80% by 2030? That to meet like 1.5 by 2050?
Yeah, so that's to meet 1.5 degrees, to prevent 1.5 degrees global warming. Anytime in the future. So the 80% by 2030 and 100% by 2050 will avoid, according to the IPCC numbers, will avoid 1.5 degrees global warming. And this will do it even better. But since we're also interested in air pollution, which is problems are accruing every single year, which is an even more urgent reason to address it faster, that's why I would have this graph, for example. I mean, if you want to meet 1.5, then the previous graph is sufficient to do that. Yeah.
What is the role of long-distance transmission? We're not talking about shiny HVDC lines. We're talking about like good old AC high voltage lines. Like the build out of those have in like achieving the kind of capacity build out that we're seeing here.
Yeah. So you would need a build out of transmission. Now there is a trade-off between battery storage or other storage and transmission. Like the more storage you can have, the less transmission you'll need. Conversely, if you have no transmission, if you have no storage, we'll need a huge amount of transmission, like including HVDC. And so there is a certain amount of transmission that will still need to be built out with, even with a lot of storage. But a lot of it can be built out on existing pathways, and a lot of it's shorter distance. Especially if you go offshore wind, it's like you're very close to where people live, and it'll be underwater too.
But is there like a trade-off in terms of embedded carbon between building, say 20 megawatt hour battery pack on utility scale versus building like 1,000 kilometer transmission cord?
Well, I think it's more of a practical consideration. I think it's a lot easier to site a big battery storage facility than it is to build 1,000 kilometers of new transmission. You just need so many permits. So I think that's really the stranglehold, and what will slow things down is trying to build out transmission. It's just a zoning issue. Whether, not ignoring the carbon, I don't know the numbers in terms of carbon, but presumably, since we're going to 100% renewables for everything here, all manufacturing will be 100% renewables, including mining of lithium. But even mining of lithium could be zero new mining, because like in the Salton Sea, which maybe have enough lithium for the entire U.S., like there's geothermal electricity plant that brings up the brine already, and you just need to extract the lithium from the brine without any new mining. So there are ways to actually mine with very little impact, and plus we'll be 100% renewable, so there won't be much carbon in that mining. Yeah.
Just wondering with this sort of scheme, because you talked about like your house or maybe Stanford in general, kind of like either microgrids or like smaller grids for community sizes, and that kind of is maybe in conflict where we could do that, or we could have very long range transmission, or a bit of both. Like, what's the kind of grid model that is able to like accommodate all these renewables, but still like maintain like energy security, but taking advantage of some of the pros of like a microgrid?
Well, we'll need both distributed solar and utility solar, because there's just not enough rooftops even if you covered all the rooftops that you could, you still need more energy, and so we will need utility scale. But we should put as much rooftop solar as possible, because there is an advantage of reducing transmission requirements, reducing fires, because why do we get fires in California? Well, a lot of them are due to transmission sparks. And so you avoid that by putting rooftop solar on quite a bit. But we will need lots of utility scale as well. So this actually represents, let's see if I have a number. Yeah, so here's the percent of wind, solar, well, WECC is the Western Interconnect, so that's the Western grid, so closest to California. Well, California's in that. And in this plan, we've got 23% onshore wind, 23% rooftop solar and 27% utility solar. And that's pretty much covering a lot of the south-facing roofs with solar in California. So even covering most of them, you'll still need utility solar. Does that answer your question? So this is kind of one mix. This is not the only possible mix for each. And the world one is averaged over all 145 countries. The U.S. is from a U.S. plan. And then we did actually all the 50 states and the different grids in the U.S. and got some kind of higher resolution results. But just because I'm running late, let me go quickly. The land area, you might ask how much land? Well, worldwide, we'd only need if you look at the graph on the left, we don't need any new land for offshore wind, tidal wave power. We don't need any new land for rooftop solar. We don't need new land for hydro in these plans, because we're not adding hydro, we're just using existing. Geothermal is pretty trivial. So the only new land is footprint for solar, utility scale solar PV and concentrated solar power. And then what we call spacing between the wind turbines. And that spacing can be used for multiple purposes. So for onshore wind for the world, it's about 0.36% of the land for spacing, 0.17% for footprint, so a total of 0.53%. For 145 countries in the US, it's 0.84%. Western Interconnect is about 0.3%. But how much land does the fossil fuel industry take? Can anybody guess for the US? 1.3%. So 1.3% of all U.S. land area is occupied by the fossil fuel industry. That includes 1.3 million active oil and gas wells, 3.2 million abandoned oil and gas wells, millions of miles of pipelines, and storage facilities, refineries, hundreds of thousands of gas stations, coal mines. If you add it all up, it's 1.3% and growing. 50,000 new oil and gas wells every year are drilled in the U.S. It's pockmarking the U.S. You can fly over North Dakota. It just looks like a bunch of, you can see all these wells everywhere. You think, you'd think it's just prairie land. No, it's not. It's just destroyed land. And so this is reduces the land use, even though people think, oh, all those wind turbines are going to take up lots of land. Well, they do take up land, but you can use that land for multiple purposes, and it's not as much land as the fossil fuel industry. In terms of grid stability, I'll just say this is a result for the Western this is the U.S. Just looking at grid stability over a couple of years, every 30 seconds, with just entirely wind, water, and solar. So I build computer models, including a weather prediction model, predict the weather every 30 seconds for several years, including solar and wind fields, and use that as inputs into matching power demand with supply. And here's an example of matching power demand, supply, and storage, and using demand response every 30 seconds with just wind, water, and solar. It's entirely intermittent. We keep the grid stable, no blackouts. This is the Western Interconnect, same thing. I'm going to skip this, but skip that. But here's the cost. What's the capital cost? So worldwide, it's $61.5 trillion. The U.S., it's about $9 trillion a year. Sorry, $9 trillion up front. And Western Interconnect is about $1 trillion. So what does that mean? Well, just keep that $62 trillion in mind. This is the annual cost worldwide. This is more important. The annual cost of energy worldwide is about $18 trillion per year. But if we electrify and go to wind, water, solar, we not only reduce power demand 56%, which means you're paying for 56% less energy each year, but the cost per unit energy is also about 10 to 15% lower. So you have a 63% lower energy cost per year, mostly due to the fact you're using less energy. So what's 17.8 minus 6.6? So it's like 11.2 trillion per year savings. What's 62 divided by 11.6? That gives you the payback time. It's about a 5.5 year payback time. So this transition, just the energy alone, payback time is 5.5 years to transition the entire world to wind, water, solar. If you add in the health and climate costs of fossil fuels, 33.6 trillion a year is the health, 32 trillion for climate costs in 2050, $83 trillion per year is the social cost of energy. So, and you go down, you eliminate health and climate costs with wind, water, solar, so you go down 92% social cost. It's less than 1 year payback time in terms of social cost. The same thing with the U.S. I'll skip that, and the Western Interconnect. By the way, I'll just say for the U.S., the annual cost of energy is 0.93 trillion, so $930 billion a year. That's how much it would cost to transition for the U.S. What's the military budget? It's like $750 billion a year. Yeah, question?
Does the previous figure include storage?
Yeah, that includes storage, transmission, generation, hydrogen. I'll just say just a couple things on policy. Oops. Really quickly. Well, we developed our first plan in 2009 for the world, we said, well, we found that it's technically and economically possible to transition by 2030 at the time, back in 2009, but for social and political reasons, that might not happen. And that's when we came up with 80% by 2030 and 100% by 2050. But little did we know, this turns out to be the scientific basis for the Green New Deal, which was a policy proposal in the U.S. to transition the U.S. to 100% renewables. There have been 8 laws proposed in the U.S. Congress and resolutions to go to 100%, but none of them have even been voted on. There are 61 countries that have committed to 100% renewables, either through laws or policies. Most of them are small countries. There are 13 countries that are near or above 100% renewables in their electric power sector. There are 18 states that have 100% renewable electric laws or executive orders. And I like to say that they're based, because we developed plans for every state, and these got promoted quite a bit. And proud to say that I think these are based on our plans. And we really motivated a a movement. I mean, we couldn't do it alone as scientists, so we helped co-found a nonprofit called the Solutions Project, where we combined science, business, culture, and community, and they amplified the plans and got policymakers involved, and then lots of nonprofits, including the Sierra Club and NRDC and Greenpeace, they all took these and went to legislatures and helped pass laws based on these science plans. So there are standing laws in California, for example, to go to 100% renewables by 2045. There are 180 cities that have laws now to go to 100% renewables in the U.S. There are over 360 international companies, including 8 of the 10 biggest in the world, the ones in blue, that have policies to go to 100% renewables for their global operations. And just to summarize, I didn't talk about jobs. We've created millions more jobs than lost. Talked about land, deaths, reversing deaths, and temperatures. Keep the grid stable, lower energy costs, lower social costs. Finally, just more information if you want more. So I think I'm out of time, but sorry to go over. But I think you asked a lot of questions. If you have 1 or 2 more questions, happy to answer. Yeah, one more. Oh, thank you. Thank you. Yeah, go ahead.
How do you think everything in Russia is going to affect all of this? Because I know the U.S. is sending a lot more, like, natural gas, right, to Europe.
Well, yeah, it's doing a couple things. One is it's actually spurring more renewable investment because countries realize they have to be more energy self-sufficient, and these types of plans make the country self-sufficient, and it's also exposing some of these energy security problems with fossil fuels and gas pipelines. So there's Biden is trying to temporarily send some liquefied natural gas. I don't know if that'll actually happen, but that's more of a temporary thing. But I think they're thinking more longer term. All these, like Germany's definitely going to move more towards renewables, even France, because half their nuclear reactors are down and they don't really have a source of gas, so they've got to go to more renewables too. So I think it'll actually help spur more renewables everywhere.